Okay, so let's do a couple examples of uh, vector addition. So we're going to be given vectors in, maybe component form, magnitude and direction form. So we're going to add vectors, find the resultant vector. So in the process, we're going to be going back and forth between the two forms. So I'll show you how we go through that. So this ship has 4 displacement vectors, and I wrote this problem to cover the 4 cases of vectors that are going to be lying on our axes and how we're going to handle them. We're still going to go through the process of writing them in component form and then adding them up, finding the magnitude and direction, but these are unique vectors. So we've got 4 displacement vectors: 100 kilometers east, 49 kilometers north, 20 kilometers west, and 100 kilometers south. So I'm going to write all 4 of these vectors in component form. Now I call my position vectors R vectors. Sometimes you'll see them in a textbook written as R, which is fine. That's just the notation I choose. Sometimes, it'll be D or L, distance for length or something like that. But for now, we're just going to say they're R vectors. So I'm going to give them subscripts: R1, R2, R3, R4. So the 100 kilometers east doesn't have a Y component. Right? If I'm traveling strictly east, I only have an X component. So I'm traveling in the positive X direction 100 kilometers. Second vector was north. So that is strictly in the Y direction. Right? So I'm writing it in vector form, it just doesn't have an X component. Or I'm writing it in component form, it just doesn't have an X component. R3 was 20 kilometers west, so this is in the negative X direction. Then finally R4 was south, negative Y direction. So these are vectors in component form, they just either only have a horizontal or a vertical component. So I'm looking for R net, I'm looking for the net displacement. So now that I have the vectors all in component form, when I add them up, my resultant vector is going to be in component form. So I'm going to have to switch that to magnitude and direction. So I'm looking for R net. I'm adding the X components and the Y components of the vectors together. So I made a little chart. I've got an X column, I've got a Y column. So I just substitute my X and my Y values for each vector, making sure I bring my negative signs along with me. Add up the X components, I get positive 80 kilometers in the X direction. Add up your Y components, 51 kilometers in the Y direction. So I've got the components of R net solved for. So I write it in component form. We need magnitude and direction. So I'm going to use my Pythagorean theorem formula to find the magnitude. 80 kilometers in for R sub X, negative 51 kilometers in for R sub Y. Calculate that. This is the magnitude of R net. This is the total net displacement of the ship. Right? We'll say the ship started here and it ended 94.9 kilometers, some direction away from the original position. So what direction did the ship travel in? So we take the inverse tangent of the Y component over the X component. Okay. So I'm going to get my calculator out, right? Hit second, tangent, negative 51 over 80. And my calculator's probably going to give me a negative sign. Right? Most scientific and graphing calculators will say that this angle is negative 32.51 degrees. What's this negative sign mean? Well, here's the situation. Your calculator only knows that you passed a negative value to the inverse tangent function. Okay? Your calculator doesn't know that the Y component's negative. Okay? It just knows that this whole number is negative. Okay? So I could have either a negative Y and a positive X, or a negative X and a positive Y, and I'd still get this same number. What's that mean? Let's go all the way back. Your calculator doesn't know whether you're talking about a fourth quadrant vector with a positive x component and a negative y component, or a vector in the second quadrant with a negative x and a positive y. Alright, so it just gives you a negative sign because it's by default it's measuring from the positive x-axis in this direction. Okay, so we have to discern whether we're talking about a vector that's pointing in that's in the second quadrant or the fourth quadrant, and so I have to look at the signs of the x and the y components to make that determination. And so that's what I did here. I draw a vector with a positive x component and a negative y component. Right, so I have to use the signs of each component to determine exactly what direction this vector is pointing in. So you don't have to keep that negative sign there. I usually don't. If you do, don't worry about it. A full description of a vector's direction is the angle and from which that angle is being measured to the vector. Okay, so I drew my picture. I know I'm a fourth quadrant vector. I like to say both. You only have to say one. Generally, this is the preferred method, right? But we are talking about a ship, you know, northeast, west, south, all that stuff. So either one of these are good. We can either say 32.5 degrees below the positive x-axis or 32.5 degrees south of east. So magnitude, full description of the direction. That's what I'm looking for. I'm looking for the angle and then a description of the direction with respect to the nearest x-axis or using cardinal directions. So we've got a similar problem, but we changed things up. The vectors, they're still displacement vectors, but they are not strictly in the x and y direction. So we actually have 1, 2, 3 vectors that are in magnitude and direction form. Right? A commuter airplane flies 175 kilometers in a direction 30 degrees north of east. So we're given the magnitude and the direction of this vector. So we're given the same, the other two vectors in the same form. So we're going to have to take all three of these vectors and resolve them into their components before we add them. So we're looking at the plane's displacement from its starting point. What I like to do, and I didn't do it in this slide, but 9 times out of 10 it will say magnitude and direction of the displacement. So make sure, just to play it safe, just to cover your bases, make sure if you're looking for a vector, you're looking for a resultant vector, write it in component form and the magnitude and direction. Okay, just play it safe. Completely describe the vector using both component form and magnitude and direction, just in case. Alright, so we've got our first vector. We're going to call it R1. Its magnitude, note the notation. I get 2 arrows there. That's just a typo on my part. Nothing significant about that. Magnitude is 175 kilometers. Theta is 30 degrees north of east. All three of these vectors, I'm going to draw them individually on an XY plane. Okay, north of east, I like that language, right? North of east, above the x-axis. So I know this is a first quadrant vector. X components and Y components are going to be positive. R2 is 150 kilometers. There it is. West of north. Right? West of north. Do not like that. So I gotta do something to make my life a little easier there. But I'm going to draw it. Here's R2. And it says 20 degrees west of north. So this is the theta that they're talking about. 20 degrees west of north. 20 degrees west of north. I don't like that angle. I don't like that angle. I'm not comfortable with it. Some people are. I'm not a big fan. So I don't want that angle. I want its complement. So when I'm resolving R2, I'm going to use this angle because it's measured from the nearest x-axis. So I'm going to take theta 2's complement, 20 degrees west of north, and I'm going to call phi 70 degrees north of west. So for R2, I'm going to use 70 degrees, this angle right here. So watch out for that. That's going to happen. They're going to give you the angle that you don't like. Find its complement so your original formulas work. You don't have to flip the sine and the cosine and stuff. R3 is another vector with just an x component, right? Theta 3 west, just west. So what's that mean? How do we draw that? R3 is west. Now I drew this angle right here from the x-axis, theta 3. And I'll talk about why I drew that theta 3. I don't necessarily have to use this angle, but this angle is 180 degrees, and I'll show you why I drew that. So resolving R1, I've got the x component, the magnitude times the cosine of my reference angle, 30 degrees. I get 151.6 kilometers in the x direction. Y component, magnitude times the sine of 30, I get 87.5 kilometers in the y direction. Every time I resolve a vector, I'm going to look back at the picture and say, did I get my signs right? X component's positive, y component's positive, I'm in the first quadrant, I'm good. R2. Again, I'm using phi 2. I like this angle from the x-axis, so I'm using 70 degrees, not the 20 that was given to us. X component, 150 kilometers times the cosine of 70 in the x direction, I get 51.3 kilometers in the x. Y component, magnitude times the sine of 70, I get 141 kilometers in the y. Go back to my picture. What quadrant am I in? I'm in the second quadrant. A vector in the second quadrant is going to have a negative x component and a positive y component. So this is how I handle these situations. I identify the quadrant that the vector's in. All of these come out positive, right? If I use 70 degrees, they're all going to come out positive. I can put a different angle here from the positive x-axis, and it'll know what quadrant I'm in, it'll give me the values and all that stuff, but I'd much rather just find the components and then manually insert a negative sign for my x component. I know I'm negative x, positive y, so I give this a negative sign. Y stays positive. R3 is west, so it's just going to have an x component, right? The whole vector is pointing in the negative x direction. Negative 190 kilometers in the x direction. Okay. What's the cosine of 180? Cosine of 180 is negative 1. So I would take the magnitude and I'd multiply it by the cosine of 180 and I'd get a negative 1. So that's another way of doing it, but for me I drew a picture and I gave it a negative sign based on the direction I knew it was pointing. Y component, there's no y component. Okay. What's the sine of 180? Sine of 180, check your calculator, it's 0. So if I took the magnitude of the vector, multiplied it by the sine of 180, I'd get 0 as well. But again, I'm not doing that. I'm not using theta 3. I'm just recognizing based on the direction that they gave me that there's no y component. Make your chart, add them up. The x components add, the y components add, and I've got R net in vector or in component form. So I've got a negative x component and a positive y component. So I'm in the second quadrant. That's how I'm going to draw my R net. Second quadrant, use my Pythagorean theorem to find the magnitude. Plug my x component in, my y component in. I get a magnitude of 245.5 kilometers. That's the magnitude, the length of this vector. Again, that's the net displacement of this plane. It started here, it went around in all kinds of crazy directions, and then it landed right here. What's this theta? What's this direction? Take the inverse tangent of the y component over the x component. I'm going to get an angle again. You plug that in there, you're going to get a negative sign. Again, your calculator doesn't know whether you're talking about the second or the fourth quadrant. Doesn't know which component's negative. Just knows that this value you pass to it is negative. So we got to describe it. Look at your picture. You're in the second quadrant. This angle is between the negative x-axis and the vector. So this angle is above the negative x-axis, or we can say north of west. Above the negative x-axis or north of west. Is my answer reasonable? I mentioned that a couple slides ago. Excuse me. I mentioned that a couple slides ago. This is larger than 45 degrees. Okay, So this is larger than 45 degrees. So that means my x component should be smaller than my y component. Alright, if I drew this right triangle with my x and y components, my x component should be smaller than my y component. This should be the larger side. Larger angle, larger side. Okay, and that makes sense. I've got a much larger y component, 228, than I do over here, my x component. Okay, so it makes sense. It's reasonable. Here's some practice. Alright, we're going to go back to this problem. Sorry. We're going to go back to this problem and draw these. Draw all four of these on different xy planes. Okay, east, north, west, south, right? Draw all four of those vectors, then add them graphically. Do the tip to tail method. If you have a ruler or something, you can kind of draw them to scale if you want. You don't really have to. Draw them up and then see if the graphical addition at least matches, like roughly you end up in the same quadrant as you do when you solve for the vector algebraically. Do the same thing here. Take R1, add R2 to it, add R3 to it, draw them, add them graphically, and then you should get a resultant displacement vector in the second quadrant. So practice that, draw your vectors, practice the tip to tail method. Just make sure your resultant vector kind of matches in direction with your algebraic solution. Okay, so I'm going to pause this, upload it, and do some projectile motion problems shortly. Okay, thanks.